And okay, so as always, now that I've started recording, please type your name into the chat so that I have your record for attendance. I'll write that here. Please type your name in the Zoom chat. So record of attendance. Okay, so all right, thank you very much. So if you remember last week, we spent some time talking about triangles, and we're going to do a little bit more about triangles today, and we'll probably move on after this week to talk about other things. But let me just recall that we had these couple of, even before we do the homework exercises, I just want to recall these couple of ideas that we talked about last time. So the triangle inequality was this first concept we talked about. We spent quite a while on it, and it says that if you have any triangle, then the sum of the lengths of any two sides is always greater than the length of the third side, right? So if I draw a triangle and it has three sides, let's say A, B, and C, then we're going to have that A plus B is greater than C, and likewise, A plus C is greater than B, and also B plus C is greater than A. So if I take any two sides and add them together, I always get something that's bigger than the third side. So this is the first result that we talked about last time, and then we had a second result, which was this Pythagorean theorem, which says that for a right triangle, so I'll draw the picture over here. So a right triangle, meaning a triangle with a right angle here, that if we label the sides here A, B, and C, it doesn't really matter how I label A and B. Those can be switched. What's important is that C is the hypotenuse here, is the side opposite the right angle. Then you have this formula, A squared plus B squared equals C squared. Okay, that's what's going to give you your right triangle. Okay, so here A and B are the lengths of the two sides meeting at a right angle, and C is the length of the hypotenuse. Okay, so these are the two major results that we did last time, and these are what's going to get used in the homework problems that I want to go over today. So this first homework exercise says a right triangle has two side lengths 3 and 5. And the question is, what are the possible lengths for the third side? And the hint is that there's more than one correct answer here. Okay, so there's more than one possibility for the length of the third side. Okay, so does anybody have any idea how we might get one of the possibilities for the length of the third side? If we have a right triangle with side lengths 3 and 5, what's one idea for what length the third side can have? Any ideas or any ideas of strategy to start?
Yes.
Yes. Princeton.
Yeah, I think the first should be the 4.
Okay. So that's one great idea, right? So our first answer is 4, right? And so how did you get the 4?
Yeah, use the Pythagorean theorem.
Right.
And using the Pythagorean theorem, you draw your right angle triangle.
Mm-hmm.
And then the 5 stand for the hypotenuse, which is the longest side.
Right.
And then the 3 will be the opposite. And then you have to find the adjacent.
Right, exactly.
So
we'll call it X.
The square of 3 will be 9, the square of 25 will be 25. And then you subtract the 9 from the 25, it will give 16.
Exactly. So
it will give 4.
Right, exactly. Perfect. So that's great. So this is 25 and this is 9. So if you solve this algebraic equation, if we're going to subtract 9 from both sides, what are we going to get? We're going to get that X squared equals 25 minus 9, which is equal to 16. And this gives us a solution X equals 4, right? So that's great. Okay, so in this case, what we're going to label here, this side is going to be 4. Okay, so 4 is definitely one of the possibilities for the length of the third side. Okay, does anybody have another possibility for the length of the third side? Is there another example, another number that you can get? So my hint is there's one other possible answer. So 4 is one of the answers, and then there's one more possible answer. So maybe also, all right, first answer here. So now if we do second answer, let me just separate all this stuff over here. So I'm going to draw the triangle again, but I'm not going to label the sides, right? So here I labeled the sides here 3 and 5. But all I told you in the problem is that 2 of the sides have lengths 3 and 5. So how else could I draw the 3 and the 5 here?
I think you add both of them.
Right. So if I drew the 3 here, and then I could put the 5 over here, right? I mean, there's nothing in the setup of the problem that says the 5 has to be the hypotenuse, right? So I have to have, so I could also have the 3 and the 5 over here, and I could call this x, right?
Oh, okay.
Right. And so then what equation do I get? Right, I get 3 squared. Yes?
S squared?
Yes, Armstrong? Yeah.
S squared?
Mm-hmm.
It's got A squared plus B squared.
Right.
Okay. S
So
squared is 5 squared
mm-hmm.
plus 9 squared.
Right, plus 3 squared, right?
S squared is equal to 25 plus 9.
Exactly. So you get 34 equals x squared. And so x, right, is square root of 34. Right, which is about 5.8 or something like that.
Yeah, 5.8.
So that's great, right? So this is the other answer, right? So I mean, you have the Pythagorean theorem, but depending on which side your x is, then you're going to get a different answer. If x is one of your legs and 5 is the hypotenuse, then you get 4 as your answer. If x is the hypotenuse and 3 and 5 are the legs, you're going to get square root of 34 as your answer. So let me just write that in the blue here. Second answer is going to be square root of 34. Okay. And now here's a question. Could I take 3 to be the hypotenuse? Like here we took 5 to be the hypotenuse, and here we took x to be the hypotenuse. Could I draw the triangle with 3 as the hypotenuse? No, why not? Yeah. So I don't think I'm getting you clearly, but what I'm
Yeah, please come on with the question, Mr.
So sorry, can I draw the triangle with 3 as the hypotenuse?
That's amazing.
Right. So let me just mute. Okay, so the point is I can't draw the triangle with 3 as the hypotenuse because I know that 3 is the longest, sorry, the hypotenuse is always the longest side. And so if I've got a triangle that has a side of length 3 and a side of length 5, then there's no way that 3 can be the hypotenuse because 3 is definitely not the longest side, right? Because I've got 5. It's possible that 5 is the longest side, and it's also possible that neither of them is the longest side, and this x is actually going to be the longest side. So I don't know, but I don't know, but in any case, I definitely know that 3 is not the hypotenuse. So we're not going to have 3 different answers here. We're only going to have 2 different answers. So the possible answers are 4 and square root of 34. All right, any questions here? Okay. So if there's no questions, let's do the second problem. So the second problem, which we talked about a little bit last time, but let's do the full answer. A triangle has side lengths 7 and 13. The question is, what are all the possibilities for the length of the third side? So maybe just to make things better, let's let x be equal to the third side. And so this question is about the triangle inequality, right? So there's going to be various equations or inequalities that need to be satisfied for x in order for it to be able to be a third side of a triangle. Like you can't have a triangle with side lengths 7 and 13 and 100 because that's going to violate the triangle inequality. So what are the conditions we need on this third side so that it will satisfy it? Yeah, sorry. Prince? Yeah.
Yes, sir.
Yeah.
Yeah, I think we can say use the right angle triangle, which is using the Pythagorean theory, and then the side which is the third side, it will be 5.
It's not quite 5. I think it doesn't come out to be a whole number if you do this third side. So remember, I haven't said anything about it having a right angle. I'm not saying that a right triangle has side length 7 and 13. I'm just saying that a triangle has side length 7 and 13, right? So it doesn't have to be a right angled triangle, right? It's just any triangle.
Yeah, for sure, because it's what I'm looking into. If we're using a 5, 2, and then the 5, like it would be the smaller side of that triangle, which
right.
it had to be 4. Yeah. We have 7, we have 13.
Right. So if you had 5, 7, and 13, what's the problem here with a 5, 7, 13 triangle? What goes wrong?
Yeah, let me try. I
Okay.
think the triangle will no longer become a right angle triangle.
Right. Well, I claim this is even worse than not a right angled triangle. I'm claiming that this is not any triangle at all. You can't have a triangle with side lengths 5, 7, and 13.
No.
And because, remember, we have this triangle inequality, which says that in any triangle, the sum of the lengths of any two sides is always greater than the length of the third side. Right? So if we go here, we have 5, 7, and 13. What do we get? Well, 5 plus 7 is equal to 12, and this is less than 13, right? And so this is a problem, right? So it means you can't have a triangle with side lengths 5, 7, and 13. Yes, I mean, the root of 120 is what you would get if you wanted it to be a right triangle. But this question actually has nothing. Sorry, let me just mute everybody so I can hear a little easier. So this question actually has nothing to do with right triangles, and it has nothing to do with the Pythagorean theorem. Okay, this is purely a question about the triangle inequality. So to Harrison, yes, the square root of 120 is one possibility, and that would make it a right-angled triangle. But there are lots and lots of other possibilities. This is not just kind of finitely many possibilities. There's going to be an entire range of possibilities for the length of the third side. So what we're basically asking here is, what are the possible values of x? So I'll write this down. So what are the possible values of x that do not violate the triangle inequality? Okay, this is really what the question is asking. So we need to know the triangle's got two sides, 7 and 13. It's got some third side, x. And I'll draw a picture, but I don't want to draw this as a right triangle, right? And that's not even a good picture. Let me try. So if I draw something like this, triangle like this, and this is 7 and this is 13 and this is x, I want to know what are the possibilities for x that are not going to violate the triangle inequality. Okay. So does anybody have maybe at the very least some condition that x is going to need to satisfy? Like in terms of an explicit inequality on x, that it's like bigger than something or less than something?
I'm looking at 6
Yep.
to B.
Princeton? Yeah.
Yeah, I'm looking at 6 to B.
6.
Yeah.
Right. So what do we need to know about x and 6? So this is good. 6 is important here. So we have x and we have 6. What relation needs to hold between x and 6?
The reason is that if we take the 13, if we take the 7 from 13,
Yep.
you will be leaving with 6.
Right. So we'll get 6 there.
Yes.
So what does that
and
mean
then,
about x and 6? So does x need to be bigger than 6 or less than 6 or equal to 6? What does it mean about x with 6?
It's equal to 6 because if you add a 6 and the 7 again, you see 13.
Okay, so what happens if you do that? If you take x equals 6, so let me say x equals 6, I'll write a question mark here. So what happens,
Yeah.
remember what the triangle inequality comes from. It comes because the shortest distance between 2 points is a straight line, right? So if I had a 7 here and a 6, right? Well, then this distance across the bottom would be 13. That's a straight line. But I could also go up to this point and down to this point, and that total distance would also be 13, right? Because I'm doing 7 and then 6. So this is actually no good, because if these 2 points are at a distance 13 from each other, then there's no possible way that I can go from this point up to this point and then back down to this point and still have the total distance be only 13, right? If the distance is 13, that has to be along a straight line, right? Any way that deviates from the straight line is going to cause the distance to be greater because you're not going directly. So this triangle does not exist. Okay. I mean, I drew it, but that's just because I lied to you when I labeled these side lengths. If you actually measured these side lengths, you would not get 7 and 6. I just wrote a number 7 and 6 there. But in fact, you can't have a triangle with side length 6. So this doesn't work. But 6 is going to be an important number. So if this side length is 13 and this side length is 7, and you know that if you go from this point to this point to this point, that better be a total distance of more than 13, then what does that tell you about this side, about x? If you want the total distance from here to here to here to be more than 13, then what does that tell you about x in terms of its relation to 6? What's the inequality sign that we want?
X is greater than 6?
X is greater than 6, exactly. So you need that x is greater than 6, because what you really need is that 7 plus x is greater than 13, right? You need, when you're adding these two sides, it has to be greater than the third side. So you need 7 plus x is greater than 13, which of course, if we subtract 7 from both sides, gives us that x is greater than 6. Okay, so we definitely need that x is greater than 6 in order to just have a triangle with side length 7, 13, and x. So whatever that third side is, it needs to be greater than 6. Okay, so now the question is there anything else that's also necessary? Is it fine to take any number greater than 6 and have this work? Or do we need another bound, another inequality?
Yeah, that over.
Yep. Yes.
Yeah,
James? James?
Yeah, the shortest side of a triangle should
Yep.
be the straight line, and the straight line equal to 13. So if we are choosing Loma, it's not because 7 is greater than 6 and 7 is less than 13. 7 is not, and that is not a straight line, right?
Well, I mean, right. So 7 plus x is not a straight line because you're doing two sides, right? I mean, every side of the triangle is a straight line, right? A straight line is just the shortest distance between 2 points. So if I take any side, if I take this 7, that's the shortest distance between this point and this point over here. That means that if I take the other two sides of the triangle, well, they'd better add up to something bigger than 7. Now, in this case, this side is already 13. So 13 plus x is certainly going to be bigger than 7. So that's not going to cause any problems, So what we saw here is also, well, 13 is the shortest distance between these 2 points because it's a straight line. And that means that 7 plus x has to be greater than 13. Now, here we have x over here, right? And so this x right here is also the shortest distance between this point and this point. So what does that tell us? So I can get from this point to this point by going a distance of x in a straight line, or I can go a distance of 13 to this point and then a distance of 7 to this point. So what does that tell us? Does that give us an inequality for x? Because we know that the shortest distance is a straight line. So what does that tell us? I claim that we get another constraint on x, not only x greater than 6, but we're going to get something else also, another inequality involving x. So any ideas? And remember, I'm stating this all in terms of geometry, but we stated it in terms of algebra over here. The triangle inequality just says that if you add up any 2 sides of the triangle, it has to be bigger than the third side. So a plus b is greater than c, a plus c is greater than b, and b plus c is greater than a. So we kind of used one of these inequalities here. We had that 7 plus x has to be greater than 13. All right. Can you write down another inequality that has to be satisfied? That's, one of these things that you get from the triangle inequality. So what's something else you can get for a 7x13 right triangle? Not right triangle, a 7x13 triangle. I claim I'm going to have x has got to be less than something also. What's an upper bound for x here? X is the shortest distance between these 2 points. So what does it have to be less than?
If x is shorter distance, that'll be less than 7.
Has to be less than, well, it doesn't have to be less than 7, right? I mean, this looks pretty reasonable, this diagram, and that this x is going to be bigger than 7. But it does have to be less than 7 plus it's going to have to be less than 7 plus 13, right? Because this x is the shortest distance between these 2 points. So if instead I get from point A to point B by going 7 and then 13, that's a total of 20. And I managed to get from this point to this point by walking a distance of 20, and that didn't even go in a straight line. So if I'm going to be able to do it in a straight line, that distance has got to be less than 20, right? Because I could do it in 20 without even walking in a straight line. So if I walk in a straight line, that's going to be less than 20. So we get here that x is less than 7 plus 13, which is the same thing as saying x is less than 20. So it turns out that this is my other constraint. So we have to have that x is greater than 6, and we also have to have that x is less than 20, right? And now really there's a third inequality, but this one doesn't matter, right? I also have to have that x plus 13 is greater than 7, but this just means that, if we subtract 13 from both sides and subtract 13, we're going to get that x is greater than -6, and this is automatic, right? Because the side of a triangle is always positive. So this condition I don't really need to include, that it's greater than -6, because we already know that it's greater than 6 even, and it has to be less than 20. So the possible values of x, if I want to write a solution, let me just erase this up here. So if I want to write a solution, the solution are the possible values of x values are those satisfying 6 is less than x is less than 20. Okay, so that's the solution here. All right, are there any questions on that? What we do is we just take each of the 3 different triangle inequalities that you get, that each side is less than the sum of the other 2 sides. Here you get something important, you get x greater than 6. Here you get something important, you get x less than 20. And here you get something meaningless, just that x is bigger than -6. That's not a constraint because we know x is positive anyway. Okay, so it turns out what you need to satisfy is exactly x greater than 6 and x less than 20. So you can always make a triangle as long as the third side is between length 6 and length 20. Okay, anything bigger than 20 is going to be no good, and anything less than 6 is going to be no good. All right, any question?
Thank you, sir. It understood to me.
Good. Anybody else? Okay, so let's move on. All right, so this is just the review. Okay, so I want to talk a little bit about similar triangles. The possible answers, lies between 6 and 20, not between 7 and 20. Between 6 and 20. It doesn't have to be an integer. It could be 6.1 or 19.9 or something like that. Okay, good. So now we're going to talk about similar triangles. So we have the 2 triangles are similar if the angle measures of one are the same as the angle measures of the other. And in this case, the picture is that one of the triangles is a dilated, that's the mathematical word, common word you just say is a scaled up version of the other one. So if I want to draw a picture of similar triangles, I might have a triangle that looks like this, and then a triangle that looks like this. And these angles are going to be the same. So if this angle, if these are like A, B, C, and this is D, E, F, and then maybe I'll label the sides also. So you usually label the side of a triangle with the lowercase letter of its opposite angle. So side A is opposite angle A. So you have A, B, and C, and you have D, E, and F. Okay. So what this tells us is that angle A in this case is equal to angle D, and angle B is equal to angle E, and angle C is equal to angle F. That's what that's what similar means. Okay. That all of their angles are equal to each other. So now, in fact, if I know already just that 2 of the angles are the same. So if I know angle A equals angle D and angle B equals angle E, then why do I automatically get that angle C equals angle F? So anybody tell me if I want to know whether 2 triangles are similar, I have to check that the 3 angles each match. So A and D are the same, B and E are the same, and C and F are the same. But let's say I just know that A and D are the same and B and E are the same. Why can I automatically conclude that C and F are the same? So this is this question here. So I claim that I don't have to actually check all 3 angles. It's good enough to just check 2 angles.
Dr. Oberst.
Yes.
Yeah, so if you're saying now, if you're dealing with a similar triangle, you know that A is equal to D, B is equal to E, then C and F have to be equal.
Why?
Because it's when you're looking at similar triangle, they have their angles at each position are all equal, right? Because
Right.
A is equal to B, A is equal to D in the next angle.
Yep.
B is equal to E, A in the next, E in the next angle. Then E, C and F are on the same side of the angle in both angles. So this might be equal.
Right, but I'm saying, let's say I'm not telling you that the triangles are similar. Let's say I just give you 2 triangles and I say that angle A is equal to angle D and angle B equals angle E. And I'm not telling you that they're similar. Why do you know that they're similar already without me even telling you that? If all I tell you is that angle A equals angle D, and angle B equals angle E, why can you conclude from that angle C has to equal angle F? Okay, I'm not telling you that they're similar triangles.
If I see that angle A is equal to angle B, the other of the two angles are equal, and that angle must be equal automatically.
Right. So why is it automatic? There's a key observation you need to make to know this is automatic.
Yeah.
Right? I'm not telling you these triangles are similar.
Sure. Let me check.
Yeah. Yeah, Prince.
If they have to be equal, then they should have the same value.
Sure. But I'm not saying they have to be equal. Okay, so maybe I'm not making the question clear.
They should have the same value.
Yes. Okay, I think I'm not making the question clear, I think. So I've given you a definition of what similar means. So similar means all three angles of one triangle are equal to the corresponding angles of the other triangle. Now I'm asking you a separate question. I give you two triangles. I am not telling you that they are similar, okay? All I am telling you is that two sets of corresponding angles are equal. So angle A equals angle D and angle B equals angle E. I am not telling you that angle C has to equal angle F or anything like that. And I'm not assuming that these triangles are similar. What I want you to say is, despite that, I want you to convince me that, in fact, these two triangles are similar, just based on the fact that angle A equals angle D and angle B equals angle E. Why is that alone enough information to conclude that the triangles are similar? Or in other words, why is that alone enough to conclude that angle C equals angle F? Yes, James? Yep.
Yeah, so you know that in a triangle, the total size of the total angle in the triangle is 180.
Yes, this is what I'm looking for.
The angle is equal to another angle. Let's take 90. Let's take for equal to the triangle. Let's take 90. The other angle, like angle A is equal to 90, and angle A is equal to the next angle, which is D equal 90. 90 have gone from both angles, right?
Right. Yeah. So that's great. And they don't have to be 90 degrees, right? But the key observation. Yes, James.
Hello?
Yes, hello, James.
Oh.
Hello, James. Yeah.
Hello?
Yeah, James Caselli.
Yeah.
Yeah.
So now we come to the next angle. Angle B is equal to angle E. And 90 have been gone away. We have 90 removed for the both sides. So that means angle C have 90. Angle F will also have 90 because it's 180 of a triangle, and all of 180, angle they have 4, right?
Right. Exactly. So let me just write this in a little bit more generality. So angle C, we know the angles of a triangle add up to 180. So another way of writing that is that angle C is equal to 180 degrees minus angle A minus angle B, right? I'm writing this shorthand because I don't have that much space, but the point is A plus B plus C is 180. So that, sorry, let me just mute everybody. So the point is that A plus B plus C is 180. So if I want to write C alone, then C is 180 minus angle A minus angle B. But I've told you that angle A is angle D and angle B is angle E, right? So this is the same thing as 180 minus angle D minus angle E, right? Because I'm assuming that A and D are the same and B and E are the same. What you want to conclude is that C and F are the same. But the point is, we know in triangle DEF that angle D plus angle E plus angle F is 180 degrees. So if I take 180 degrees and I subtract off angle D and I subtract off angle E, what I'm left with is just angle F. Okay? So what this tells us here is that angle C, going through all of these equalities, is equal to angle F. Okay? So this is why you can conclude it. If I know that A equals D and B equals E, by using these equations and the fact that the angles add up to 180 degrees, I get for free afterward that angle C equals angle F. Okay? So what that tells us is that if you want to check whether two triangles are similar, you don't actually have to check all three angles, right? It's good enough to just check two angles, it's good enough to just check two angles. And if you check that two angles are the same, then the third angle follows for free. Okay. All right. So does this make sense? Any questions?
So yeah, sure. There's something I want to get clear. So based on the question you are giving, if you want it to be like angle C equal to angle F, it's just by subtracting the other angles from the angle which is given.
Yeah.
To get because it's what you did. You subtracted all of the angles from angle C to give you angle F.
Yeah.
So it's just about subtracting the zero angles.
Yeah, exactly.
So
it's just about subtracting those angles.
Yeah. If subtracting the zero angles, so we are using the angle of 180 degrees.
Right. Because we know that we did last time that the angles in a triangle add to 180 degrees. So this we proved last session.
Okay.
Yeah.
Thank you.
You're welcome. Okay. So once you know that they add to 180 degrees, that tells us if you know two angles, you know the third angle. That's really what's happening. Yes, Ed?
Yeah, I have a question. Yes, because I know that similar triangles, they are not congruent.
Right.
Right?
Correct.
They are similar.
Right.
If they are congruent, that is, they are equal. So I know the criterion to know whether a triangle is similar and is not congruent.
Right. So we're only checking angles, right? If you want to check that triangles are congruent, you have to check the sides somehow. But everything we're talking about so far is just checking angles, right? Angles will tell you that the triangles are similar. If you want congruent, then you need to say something about the sides. And so far, we're only talking about angles.
Yeah, sure.
Yes?
Yeah, based on the question asked, I want to just derive my question from the two to ask. Can a similar triangle be formed in a congruent way, or can it be congruent, similar triangle?
Yes, congruent triangles is a special case of similar triangles. So if you have two congruent triangles, they are similar. But the other way around is not true. If you have two similar triangles, they might not be congruent.
Okay.
Yeah. But yes, any two congruent triangles are also similar. Okay. So let me just say also that similar triangles here, the other important property of them is not just that they have their angles the same, but they also have what's called a common ratio. And what that means is that when we have the side lengths, what does this common ratio mean? It means that the ratios of the sides are equal no matter which side you're talking about. So in this case, we would have that A divided by D is equal to B divided by E, and this is equal to C divided by F. Right? So the triangle has a size. Let's say this triangle is stretched by a factor of 2 from this triangle. Well, what that tells us is that A over D is going to be 1/2 because D is twice as long as A, and B over E is also going to be 1/2, and C over F is also going to be 1/2, right? But in particular, these ratios are all the same. So whatever the ratio of one pair of corresponding sides is, the ratio of the other pairs of corresponding sides, it's like B over E and C over F, are all going to be the same. So this is true. This here, that A over D equals B over E is equal to C over F. This is true for similar triangles. Yes, James?
Is it possible to find one side of an angle? But as like example, you have the value of A given, the value of D given, the value of B, the value of E, and the value of C given to find the value of F. Not looking at it, but how to solve it.
Yeah, so let's do that. Let's do an example on the next page. Okay, so let's say that I'm given two similar triangles, So let's say I'm given two similar triangles and okay, if I'm given this diagram of two similar triangles and I have 3 and then an 8 and a 9 and an X. So 3, 8, 9, let me say, and 5, or 3, 8, 9, and 6. Yeah, maybe, no, let's call it 5. So let's say I have that. And let me give these sides names. I'll call them X and Y. And so the question is, calculate X and Y. So I'm telling you that these triangles are similar, right? So, and what we know is that similar triangles have this common ratio, right? The ratios of the respective sides are all equal, right? So what is the common ratio of these triangles based on how I drew them? Well, I have a side length 3, right? And I have a side length 9. So the ratio, the common ratios here tell me, right, that 9 over 3 is equal to what? I mean, I know it's 3, but what is it equal? What other ratios is 9 over 3 equal to in terms of the other sides of the triangle?
To be equal to y over 5.
Careful, it's not going to be y over 5 in this case because I started with the 9 divided by the 3. So I've got to keep the triangles consistent. So 9 over 3 is...
Yes.
Yeah. James, are you raising your hand?
3.
Yeah, well, it's 3. Okay, so of course this is 3. But what other ratios is this equal to? Yeah, James? Hello? Yeah, Harrison?
Yeah.
Yeah.
X.
8 over x, yes. So it's 9 over 3 is going to be the same thing as 8 over x, exactly. And that's also the same thing as... yes, I'm not getting you very clearly.
Yeah.
Yeah. Yes, hello? Prince, yep.
Hello.
Yes, Prince, what else is this equal to?
Yeah, it will be 5 over y.
5 over y, great. Okay. Okay. Great, so it's going to be 8 over x and 5 over y. And so now we can just solve. So this is easy. So 3 equals 8 over x. This multiplying by x becomes 3x equals 8. And this becomes x equals 8/3. And then also 3 equals 5 over y. This becomes 3y equals 5. And this becomes y equals 5/3. Okay, so once you have the common ratios set up, then it's easy to solve for the other sides. Okay. All right, so we have this. We have 8/3 and we have 5/3, our x and y. We can solve for those because they're similar triangles, and we can calculate the common ratio, right? In this case, that common ratio is 9/3, which is 3. You could have done it with 3/9 also. That's fine. You would just have that 3/9 equals x over 8 equals y over 5. And you would get the same answer because that's all of these equalities just flipped. It's not going to change your answer. Okay. All right. So any questions on this? Yes,
Yes, sir. A question.
Yes, question, Prince. Yep.
Yes. Yeah, Prince. The first one we saw, we have x is equal to 8 over 3. Can we substitute the value for x here, which is 8 over x? Can we bring the 8 over 3 here for this x value to find the same thing? Can it be done at that?
Yeah, I mean, you're just saying, can you write down the answer? Yeah, x here is equal to 8 over 3, and y here is equal to 5 over 3, right? That's the solution. Is that
No,
maybe I'm not understanding?
Yeah, one saying we have 9/3, which we got 3, which is equal to 8/x, and then we'll find the value for x, which will equal to 8/3. That is the first answer we got. Now, in this case, we are already found a value for 8/x, which is x. We are already found a value for x. Can we substitute the value for x, which is 8/3 here to find y value?
Oh, sure, if you want to, yeah. I mean, sure. If you do this, if I substitute 8/3 here, then you're just going to get the same equation, though. You're going to get that 8/8/3 is equal to 5/y. And this simplifies, 8/8/3 just simplifies to 3. So you're just going to get 3 equals 5/y again, and you're going to solve the same equation. So it's fine. It does work. Yeah.
Okay.
Yeah. Yeah, so that certainly works. Okay, other questions? Okay. All right. So let's let me do this for a second. Okay. So I'm going to skip this for now because so you can use similar triangles to do another proof of the Pythagorean theorem, but I think I'm gonna skip it for the time being because I want to make sure we have time to get to everything else. And maybe I'll just save this for next week. So let me skip the proof of the Pythagorean theorem. Yeah, so I want to talk about the total angle measure of an n-sided polygon. Okay, so we know something that we know that we did last time is that the angles of a triangle add to 180 degrees, right? This is something we know. We showed this last time. So now the question is, what do the angles add to when you have a polygon with n sides, right? So a triangle is a polygon with 3 sides, but you could have a quadrilateral or a pentagon or a hexagon. And we want to know what is the total sum of the angles in one of these larger polygons. So let's begin with the example of a pentagon. Okay, so I'm going to draw a pentagon. It's not going to be a regular pentagon. It's going to just look like this. Okay? So I drew a pentagon, right? It has 5 sides. And I want to know, what is the sum of the angles in this pentagon? Well, the trick that you can do, and this is a lot of times what you do whenever you have anything involving polygons in geometry, you always just try to reduce it to the case of triangles. So what I can do here is I can take any point here in the middle of the pentagon, and I can draw a bunch of triangles. I'm just going to draw the lines from that point to each of the vertices of the pentagon. Right? So what this does is it splits the pentagon into 5 triangles. Right, so when I do this with the pentagon, it splits the pentagon into 5 triangles. Right, okay, so 540 is the correct answer, Princeton. So I'm going to just try to remember how to derive them. To show how to derive this. Remember to please put your... Okay, so... All right, so it splits the pentagon into 5 triangles. Now we know that each triangle has 180 degrees, right? So the angles, so the 5 triangles, these total 180 degrees each, right? So if we add up all of the angles in all of these triangles, right? I just take every angle here. Boom, 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 boom. Right, so adding up all of the angles gives 180 degrees times 5, which is going to be 900 degrees. Okay. So you split the pentagon into 5 triangles. That's going to give us 900 degrees. But remember, what we did to get this 900 degrees was using all of these angles. So not just these angles around the outside, which are giving the angles in a pentagon, but also all of these angles on the inside. And these things on the inside don't contribute. But when I look at all of these angles on the inside, so these 5 angles here, what do these angles on the inside have to add up to? Because it makes a full circle, right? When I add all these angles for the triangles. So what do these angles add up to on the inside?
Can I transfer?
Sure, yes. Yes, Prince?
Yeah. Can we say add up to 360 because can we say add up to 360 because the way in which everything has been connected based on the angles in circle? Can we say equal to 360?
Yep, exactly.
Question.
Yep, that's exactly right. So of this 900 degrees, 360 degrees are in the interior.
So Athena is 360.
Exactly, that's correct. Okay, so of this 900 degrees, 360 of them are in the interior, right? They're this circle in the interior. So what's left is the sum of the angle measures in the pentagon, right? So what's left is 900 degrees minus 360 degrees, and this is 540 degrees, right? And this is the sum of the pentagon angles. Right? Because when we're adding up all the angles in the pentagon, we're just adding up what's going on at the corners of the pentagon. We're not adding all of this stuff in the middle, right? But when we draw all of these lines, we have a total of 900 degrees, but 360 of that is stuff that's in the middle. So we've got to subtract that off. And what we're left with is what's left around the edges. And that's going to be 540 degrees. Okay. So 540 degrees, as Princeton wrote in the chat, this is going to be the sum of the pentagon angles. Okay. Is that okay? Any questions?
Obers?
Yes.
Yeah.
Yeah. How do we derive 360 degree to be the sum of the interior angle?
Because the interior angles form a full circle, right? So the interior angles form a full circle. James, Ba? James, you want to say something?
Yes.
Yep.
Yes. Wisdom. I think the reason why we got the 360 is that the total distance around the circle is measured 360. And if you're looking at the point in there, in a pentagon there, you will see that an angle is measured there. So it carries around the circle there. So it creates another circle within there. So the circle that's created is total up to 360.
Right. Let me draw this more clearly. If I draw all these angles together, they form a circle, right, in the interior. It's a full circle. And this is how degrees are defined, right? Degrees are defined as a circle is 360 degrees. That's what a degree means. It means it's 1/360th of a circle. So when we take a full circle, that's automatically 360 degrees, like Princeton said. Is that better?
And another way to do that, if you're using your coordinate, if you're using the full coordinate, if you take the first one, will measure 90 degrees, second will measure 180, third will be 270, and then the last will be at 360. You can also use that method.
Right. You can say a right angle is 90 degrees, and you can add up 4 right angles. That gives you a full circle. But yeah, anytime you take the angles that make a full circle around a point, however you do it, it's always going to be 360 degrees. So James says each interior angle will be 108 degrees. That's true if they're all equal. But I didn't draw this pentagon with equal angles. These angles are all different. I don't know what they are, but they still have to add up to 540, right? It doesn't matter whether they're equal. If they're all equal, then yes, you divide by 5 and you'll get that each one is 108 degrees. But even if you have an irregular pentagon, meaning something that the angles are not all the same, and the sides are not all the same, then you can still get that the sum of the angles is going to be 540 degrees. Okay. 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 So this is how we do it. Let's talk about this in general. So what happens if instead of a pentagon, we have an n-sided polygon, right? So if we take a point in the center and connect it to each vertex, just like what we did over here, well, for a pentagon, we got 5 triangles. So in general, we're going to get n triangles. So this is going to divide the n-gon into n triangles. And so what's the sum of the measures of the angles in an n-gon? Well, we start with the total. So if we draw all angles like before, so if we draw all the angles, we draw all the angles and add like before, what do we get? We get n triangles. So we're going to get 180 degrees times n. This is the kind of total sum. And then again, we're going to have to subtract off, no matter how many sides we have, all of these triangles are going to meet in the middle. We're still going to have a full circle of these angles that don't count toward the angle sum. So we're going to have to subtract off 360 degrees. This is the kind of interior circle. And so the answer here is just going to be, 180 degrees times n minus 360, but I can also use the distributive law if I want, and I can write that as 180 degrees times n minus 2. Okay, so this is the full sum of the angles in any polygon. It's always going to be 180 degrees times n minus 2. So just examples. If n equals 3, you get 180 degrees times 1, which is 180 degrees. We already know this is a triangle, right? You have 180 degrees for a triangle. If you have n equals 4, a quadrilateral, you're going to get 180 degrees times 2, because 4 minus 2 is 2. This is going to give you 360 degrees. N equals 5 will give you 180 degrees times 3, which is 540 degrees, and so on. So if you have a hexagon, you'll get 720 degrees, and it keeps going, okay? So all that you have to do is the same thing, right? If I've got a hexagon, just to draw another picture, if I have a hexagon, I take a point in the middle. If I connect it to all of the vertices, then now the hexagon's divided into 6 triangles, and the interior angles will still form a circle, right? So you can do this with any number of sides that you want. And you get this formula for the total angle sum of an n-sided polygon, and it doesn't need to be regular, any n-sided polygon, and that's going to be 180 degrees times n minus 2. Okay? This is the derivation. I just derived the formula for you, right? The derivation is you draw all of the angles, you get n triangles, so that's 180 degrees times n, and then you subtract off 360 degrees because those angles don't count in the middle for the interior angle sum. And what you're left with when you pull out a factor of 180 degrees is 180 times n minus 180 times 2. That's 180 times n minus 2. Okay, so that is the derivation that I've just shown you. Okay, is this okay? Questions?
Yeah, sure. This,
yes, Prince.
I have a question, sir.
Mm-hmm.
I want to know as well. We have a two-side polygon. Do we have, or do two-side polygon exist?
Two-sided polygons don't exist because a two-sided polygon is like, the angle sum would be 0 in that case, right? And it just means you can't draw a two-sided polygon, right? It's just going to be, you're going to draw a line, and then you have to, a two-sided polygon, if you had like 2 vertices, it would be like you draw a line from one to the other, and then you draw the same line on the way back, and like the angles would be 0 degrees. You can think about it. But generally, you know, when you talk about polygons, you're always talking about at least 3 sides. Yeah, so
Okay,
two
so it
sides,
means
two
from
sides and
three-
one side don't really make sense. It's got to be at least 3 sides. But 6 is fine. I just didn't write it down. But yeah, n equals 6, you would have 720 degrees. Yeah.
The Obers?
Yes.
Yeah, deriving the formula for finding the sum of the interior angle. There are 2 that we used. What was it? 2 minus n minus 2. It is constant.
Yeah. Oh, so you want to know what? Yeah, I mean, 180 times n minus 2 is the formula. So do you want to know the formula for finding each interior angle in a regular polygon? That's the next slide. Yeah, so this is the formula, right? So let me just rewrite it clearly. So the formula is that sum of interior angles of an n-sided polygon is 180 degrees times n minus 2. Right, that's the formula. Okay, any questions?
My question is,
Yeah,
the
James?
2 that we get in our formula,
Oh, sorry,
it is
Marcus?
constant? It is something that we derive, or it is something?
What do you mean is it constant? The 2 is, yeah, the 2 is constant. Sorry, too much feedback. Sorry. The 2 is constant. Yes. The 2 is, it's always a 2. Yeah, it's always 180 degrees times n minus 2. The 2 is always there no matter what size polygon you have.
Okay, even myself having some misunderstanding on that. It's okay now.
Okay, good. So in the chat, there's what's the formula for each interior angle? That's what we're going to do for the last slide here. So a regular n-gon is a polygon with n sides such that all of the sides are equal and all of the angles are equal. Okay, so from the previous slide, well, so what do we have? We have, you know, total angle measure of regular n-gon is equal to 180 degrees times n minus 2. So then we get that each angle, well, you've got n angles, right? So each angle measures, well, what do you have? You're going to have 180 degrees times n minus 2, and then you're going to divide this by n, right? Because you've got n different angles, and the measures have to all be equal to each other. So each angle measures this 180 degrees times n minus 2 over n. And what is this going to be? We can simplify this. I'm just going to write this as 180 degrees times n divided by n minus 180 degrees times 2 divided by n. And that's going to be 180 degrees minus 360 degrees divided by n. Okay. Yeah, so this is it, right? So we get 180 degrees divided by 360 degrees over n. So doing the pentagon example, if we do n equals 5, we get 180 degrees minus 360 degrees divided by 5, which is 180 degrees minus 72 degrees, and this turns out to be 108 degrees. Okay, so this would be an example for a pentagon. Each of the interior angles for a regular pentagon measures 108 degrees. Okay. All right. So yeah, so that's how you get your formula. And so you can plug in whatever your favorite number is. If you wanted to take a 10-sided polygon, decagon, then you get 180 minus 360 over 10, which would be 180 minus 36, and that's going to be 144. Okay, so this formula works for any n. And this tells you how to find the number of degrees in the angles of a regular n-gon for any n. Okay. Any questions? Sorry, one second. Jen, show them the loose metal thing also. Yeah. Sorry. Okay. So questions on this?
No.
Questions on this?
Yes.
Mm-hmm.
Yes.
Yeah, Marcus?
Yes.
Marcus?
Yeah, thank you very much, Andrew. At least this one is this is my first time seeing this formula. But we have a couple of, especially the interior angle and the interior and exterior angle. We have other formula for it. I think you may know. But I want to know whether, like, for this formula, it determines whether the n is nonagon or datagon. You replace it with the n within the formula.
Correct.
Oh, okay.
Correct.
Yeah.
Okay.
So you can do this with exterior angles also. Sorry, I'm getting feedback. Sorry. So you can do this with exterior angles also. It's a different way of deriving this. It's not how I did it. I like making everything in terms of triangles, but there are ways to talk about this with exterior angles also. It's not the approach I took today, but we can talk about exterior angles some other day. Okay? But for this is the formula, and you derive it by drawing a point in the middle and dividing your polygon into a bunch of triangles. Okay? So let me just close because we're out of time. So let me just close with the homework. So first one is a question about similar triangles. So one triangle has side lengths 4, 6, and 9. Another triangle is similar to this one, and it has side lengths 8 and 12. And the question is, what are the possible side lengths for the third side? And it's a little tricky. I'm going to say again, the hint is that there's more than one possibility. In fact, in this case, there are going to be 2 possibilities. Okay, so you can think about this. Why are there going to be 2 different answers? And then the second question is to calculate the missing angle in the following diagram. So I'm going to draw the following weird-looking quadrilateral, looking like this. And I'm going to have these angles here. And so this angle is going to be 20 degrees. This angle is going to be 60 degrees. This angle is going to be 15 degrees. And so then the question is, what is this angle that I've drawn over there? Okay, so you're going to calculate the missing angle over here. And then the first question is, we have a triangle with side 4, 6, and 9, and another triangle with side lengths 8 and 12. That's similar. And I want to know what's the length of the third side of this. So you're going to have to use the common ratio of similar triangles in order to get that to work. Okay, and we'll save the proof of the Pythagorean theorem with similar triangles. We'll save that until next time, which will be next week. So next week, we'll discuss quadrilaterals, and I'll say, and do Pythagorean theorem proof. Using similar triangles. Okay. All right. So thank you for paying attention and for coming this week, and looking forward to next week, which is the 22nd. We will meet, even though it's getting close to the holidays. We're going to skip the week after that, but we will have a meeting on the 22nd. Okay. Any last questions? Okay. And sorry, you showed him the dent also? The dent in the pipe? Yeah.
It's actually coming out of the hole.
Okay. No, I'm still on. Sorry. Okay. Okay. All right. Any questions? Okay. So yes, James.
It's not really a question, but I just want to tell you thank you.
All right, you're welcome. Most welcome. Let me stop the recording.